Yeah, I can very quickly talk around this without. Yeah, I mean, I'm fine. I'll show the slides were anyway just for fun. So yeah, basically about the. I want to talk today about the EIP 7928, which is so-called block access list, and it's a step towards parallel transaction execution in Ethereum. And I myself, I'm Igor, I'm the CTO of Gateway. We're doing the infrastructure mostly, but in my past life, I was an active execution client developer. So these kind of APIs are very close to me. So basically, right now, the EVM is quite fast, but it's very limited towards what a single core of your computer can do, right? That means that you can go only as fast to scale the Ethereum, and if we want to scale the L1, at some point we need to use multi-core computing. And of course, EVM by itself doesn't have any primitives for any kind of a parallel computing, which makes it more difficult. But in the end, there is one big reason usually why the parallel computing is difficult, and the reason is called shared state. But basically, if you can imagine, if we have two like blockchain transfers for 4 independent wallets, which have nothing to do with each other, then parallel is easy. You can apply them in one order, in another order, in parallel. They don't touch each other's state. In the end, if both are applied, you will get the same state back. The problem becomes when there are certain dependencies. That means that, for example, one smart contract does another smart contract. And here we have a little bit an unfortunate design decision with ERC20, where, for example, balances of the tokens, they are in the storage of the same smart contract, of the stablecoin smart contract. And that means that as soon as you have popular stablecoin, like let's say USDT or USDC or something like this, then a lot of transactions are touching them in one shape or form, immediately you get into this conflict. Like looking back, we did actually, like I think back in 2020 or something like this, when I was at Aragon, we did an experiment, a very naive experiment in parallel transaction application on Ethereum mainnet. And basically we thought that, okay, we'll figure out, and if 2 transactions don't touch the same smart contract, we drew the line there, then we apply them in parallel. If they do, then we back off one of the transactions. And turns out we only get like 10% improvements on performance, and when we started looking up why, there were 2 reasons. One was USDC, and another was Uniswap, because these 2 smart contracts were like with most of the traffic on Ethereum way back then. So that's why in here it's much more smarter to go on the storage slot level and not on the smart contract level, because again, if there are no dependencies between storage slot of the same smart contract, you can still apply this thing. So we already have an EIP around storage slot usage, which is EIP 2930. I don't know if anybody even heard about this, but it's when we introduced warm versus cold storage, there was this access list EIP that is, I would say, was tremendous success. As of like we as an RPC provider only have one case when we had to enable that for any of our customers. So it was only one customer who was actually using this. And the problem with this, that it was opt-in, and basically no wallet used it, and it's also like an optional thing. So now comes EIP 7928, that unlike the old EIP is not optional. It also comes from the block builder of the block, and it's actually, during the execution of the block, it generates all the dependencies. Basically what EIP means is that with a block, you ship an extra metadata as soon as the block is built, and this metadata is indexed per transaction, and on each transaction level, you can basically see which storage slot attached, which storage slot were written to, yada, yada, yada. By itself, it doesn't solve anything for parallel, right? But it gives enough information that if you have this meta information already with you, you already have the decision made on how to apply transactions. You can use multiple cores, you might not use multiple cores. You can pre-warm some, I don't know, disk cache, which is another issue with the EVM and stuff like this. Of course, there is no magic. Somebody needs to come up with this metadata. So this metadata is, and to come up with this metadata, since again EVM doesn't have any parallel primitives in it, you still need to first time create the block sequentially. But for this, we have proposer builder separation, right, where the block builders, and with EPBS it's even better, where the block builders can be very powerful, so they can afford to actually do the block once for basically on powerful hardware, figure out this list, and then after that, basically go and send to everybody. And then everybody who runs the node at home, like RPC nodes or even just normal validators, they can already use these things like the parallel lists to optimize the performance. So for the L1s, basically, what you're getting at is that you're getting parallelism for those who are not built this block, but on the block propagation level, so it should help with the sync of the nodes. You also have an interesting part, because part of the research group back then, what I was a part of, was the stateless Ethereum group. That means on how do we basically sending all the necessary state to other nodes so they don't have to keep the state. They can immediately execute transactions despite of, and check the state root regardless of the previous history. So this block access list is a relatively trivial part from there to go to so-called witnesses and making sure that basically you can achieve the stateless RPC nodes or the stateless nodes basically on the Ethereum side. So what's cool for L2s today already, because L2s, a lot of them have centralized sequencers. So on the sequencer level, you don't change much because basically it's your block builder. It has to figure out the dependencies. But why it's exciting for some of the teams that I've seen who does L2s is actually there are two things. One thing is that you have a much faster RPC sync and much easier RPC sync and using multiple cores, which is nice. And again, since one of the goals of L2 is performance, the quicker your RPC node catches up to your sequencer, the quicker it looks like that it's the chain works. And the second interesting thing is that, again, Jordi mentioned a lot about the proving here. So provers also use witnesses, and ZK is also a highly parallel process. So any kind of meta information that we can send to ZK provers to help them to use parallelism could also reduce the latency of ZK proof generation. Again, that's basically a very quick overview of the EIP. So a little bit of extra meta information on the blocks that will allow consumers of this block to use multi-threading and multi-threading to consume it. A little bit more work for the block builders and a little bit of more extra bandwidth. But again, it comes with it's a very nice first step towards more parallel EVM execution. Yeah, that's it from me. Thank you so much.